So is it audible? Is it audible? Okay. So we'll solve one more problem based on vibrating string, that is the wave equation. So in the case of wave equation, right? So we proved that the wave equation, right? So which is nothing but the solution of the differential equation given by, so dou square u by dou x square 1 by c square of dou square u by dou tt square. So this is actually the wave equation actually which we have proved, right? 1 by c square is here. Yeah. So you can take it anyway, so it's just a constant. Then actually, so this wave equation, based on this actually, we have solved the general equation of the, or the general solution of the wave equation. So that is u of x comma t value we found, that is u of x comma t. So this is the most appropriate solution of this is c1 sin px plus c2 cos px getting multiplied by C3 sin CPT plus C4 cos CPT, and this is the most appropriate solution actually which we have selected. And then based on the initial conditions for this particular equation, we will be solving problems based on that, right? So here note down one more problem. A tightly stretched flexible string, a tightly stretch flexible string has its ends fixed at x is equal to 0 and x is equal to L. Has its ends fixed at x is equal to 0 and at x is equal to L. So at two different locations actually it was fixed. At time t is equal to 0, the string is given a shape defined by, at time t equal to 0, the string was given the shape of, given by the equation f of x is equal to mu x into L minus x. Mu x into L minus x, where mu is a constant and then released. And then released. Find the displacement of any point. Find the displacement of any point at a point x at any time t greater than 0. So this is the problem statement, right? So here what he asked us is, so for this particular solution, whatever we have derived, based on assuming that the final solution y is nothing but capital X, which is a function of x, and capital T, which is a function of t. So this kind of solution actually initially we assume, and based on that actually we proved that this is going to be the solution of the differential equation given by this, which is nothing but a one-dimensional wave equation, right? So the dimension is represented by this u, or actually here in this case y. You can use any value. So u or y, with respect to time it is changing, with respect to x it is changing, and the final solution is coming out to be this way. Now for that actually it is exactly the same problem what we have solved yesterday, but the difference that is going to come here is the initial displacement whatever he has given is f of x is equal to mu x into L minus x. But earlier actually in the problem statement, so in the previous problem what we have solved is this is going to be some constant a into sine n pi x, so and sine of CPT or cos of CPT, like that actually it is there. So this one is completely different. So here actually if it is not going to be a sine or cosine, then this one will have n infinite solutions. Infinite solutions are going to be there for this kind of cases. So that's why actually we will be taking this kind of case. So the initial condition u of 0 comma t is always equal to 0, or y of 0 comma t is always equal to 0, and y of L comma t is also always equal to 0. That is one more case. And another case is the initial displacement is given this particular shape, where this shape is given by f of x is equal to, so mu x into L minus x, mu x into L minus x. Got it? So mu x into L minus x, and then so based on this actually let us solve this. So try to substitute the boundary conditions, and can you give me the final solution what we can get it? So the way we have done in the previous one. So y of x comma t value, substitute the initial conditions, and then I will try to get this equation. So one more is dou y by dou t is equal to 0 at t equal to 0. This is one more. That is, initially this was under rest, right? So there is no vertical velocity initially when we have kept like this. So that is total 4 conditions. This is 1, this is 2, and this is 3, and this is 4. Now out of all the 4 conditions, you have to start with this one, that will be most easier, then with this one, then the second one, and then this one, and finally this one. So this will give a unique solution for us. Can you tell me what is the final solution you have got? Y of 0 comma t, take the first condition. So if you substitute 0, so instead of x it is 0, then it is going to be C2 cos px, C3 sin CPT plus C4 cos CPT equal to 0. Hence, it implies C2 is equal to 0. That is one condition. And then y of xt is going to be C1 sin CPT, sin px, C3 sin CPT plus C4 cos CPT. So this is the remaining equation. Once you substitute Ct is equal to 0, then y of L comma t. So this is also always equal to 0. Now if you, before that actually you can easily solve it. That is dou y by dou t, first you take it. And then this is C1 sin px. Derivative of this is C3 into Cp into derivative of sin is cos Cpt plus C4 into Cp into derivative of cos is minus sin CPT, and this is again equal to 0. So at t is equal to 0. That is at t is equal to 0. So if t is equal to 0, then this is going to be 0 and this part will be C1 sin px and C3 Cp cos Cpt. So cos Cpt value is 1. Now this value is coming out to be 0. So obviously C1 can't be 0 because if C1 and C2 both are 0, then the solution is 0. So which is rejectable solution. Why we take a derivative which is equal to 0, right? This is the condition. Here actually the problem here it is we have total 4 different arbitrary constants. Now to solve for 4 different arbitrary constants, you should be having at least 4 different conditions. Those conditions are, one condition is this one, 0 comma t, another condition is this one, and another condition is the initial displacement. Now, one condition is still you need to identify so that you can solve for the arbitrary constant. So one more condition is, initially there is no velocity, right? At t is equal to 0, we have kept like this and then leave it. Yeah, so why I have taken at t is equal to 0 is, initially when I leave it like this, dy by dt value, I am holding still like that. That time actually the velocity is going to be 0, right? When I leave it, then it started moving like this. So that time actually when it is moving, then I cannot take as the initial condition. So the initial condition is, the initial velocity is 0 and initial displacement in the vertical direction is given by this equation. So 2 different conditions you can identify based on this. Got it or not? Initially there is no velocity, right? There is no vertical movement of the particles there. So that's why actually the velocity value at any point at t is equal to 0 is coming out to be 0. Understood, Deepak? No, not only at the center. So it is independent of x, right? Dy by dou y by dt at t is equal to 0. It is independent of x. So dou y by dou t value, let us say this is g of x comma t. It may be a function of x comma t, obviously, right? So at x comma t, here I am talking about at t is equal to 0. It may be independent of, right, the x. Got it or not? So here actually the derivative may be function of x comma t, but at every point it may be having different velocities once I leave it. But before leaving means at t is equal to 0. So this at t greater than 0, here the particle will be having a different value, here the particle is having a different value, here the particle is having a different value. That means at every point the velocity is going to be different, but before leaving every point is stable, correct or not? None of the points are moving if I just hold it like this. So at every point the velocity is going to be 0. That condition I am making use of it here. Is it clear, Deepak? Yeah. So then actually, so this condition, so this one obviously, so C3 has to be equated to 0. So C3 equal to 0. So C1 can't be 0. And then the remaining conditions are, so that is C1, C4, sin px, cos cpt. That is the final solution. So that is y of x comma t is equal to C1, C4, sin px, cos cpt. So this is the solution we have got. Now, yeah, note down till this point, I am going to erase it. Yeah, so I am going to rewrite this anyway. I have erased it, yeah. Done? Now here, so y of x comma t value, so this is the solution, c1 c4 sin px cos cpt. So this is the solution. And then we have used this boundary condition and we have used this boundary condition. And then we will be using this boundary condition, that is y of L comma t is equal to 0. So y of L comma t is equal to c1 c4 so sin pl cos cpt. This is again equal to 0 because at this point also there is no vertical displacement, obviously. So here this point can't be 0. So the only C1 and C4 also can't be 0 because actually if C1 or C4 are actually it's a one constant. If this constant is coming out to be 0, then the solution will come out to be 0. That is of meaningless. That is a trivial solution. CPT, it won't be 0. Why? Because this is a cost value and it is independent of the displacement L. So here L actually we are putting it. So this part obviously cost value, this can't be 0. The only possibility here it is sin PL equal to 0. So this you can write as sin of n pi. So if it is sin n pi, it implies PL is equal to n pi or P is equal to n pi by L. So if I replace this value, y of x comma t is equal to C1 C4 sin n pi x by L into cos of n pi ct by L. So this is the solution. Now in this particular solution there is one more last boundary condition which you can use to find out this arbitrary constant. So I call this as, so this is f of x, or actually this can be treated as some constant Bn sin of, or just I call as B, sin of n pi x by L into cos of n pi ct by L. Here actually you need to understand one important factor. So in case of differential equations, suppose if y1 is a solution and y2 is a solution and y3 is a solution for a differential equation, now the sum of all the solutions is again a solution to it. That's what we call as a master solution. That master solution ideally we call as the complementary function, right? Now here this master solution will be having n different solutions. Now see this is a constant and this is n value is there and here also n is there. For different values of n, you will be having different solutions for it, right? Correct or not? Got it or not? For different values of n, there is a different solution. Now the sum of all, so that is sigma n is equal to 1 to infinity, right? Or 1 to n, keep it like that. Now 1 to n, Bn sin n pi x by L is equal to cos n pi ct by L. So this is y of x comma t is the general solution. Is this understood or not? Why we have kept this sigma? For different values of n, there will be different solution. The sum of all together we call as a master solution. That master solution for this wave equation is this one. Now this format actually why we are bringing into picture it is suppose if you have given a sine moment or a cosine moment for this particular initial displacement, then actually the same thing is moving like this. But suppose if you have given non-sine or non-cosine, then actually let us say, suppose if you have given this kind of displacement, let us say. So if this is the kind of displacement, this is no more a sine wave. This is kind of a triangle. Now this triangular shape can be converted into a sine form or cosine form, correct or not? And the method of converting the sine form and cosine form we call as the Fourier series. Now this particular waveform, if you have given a non-sinusoidal wave, what happens is this is going to generate this kind of wave. So this is one wave, and this is another wave, and this is another wave, and like this actually you are going to get infinite number of waves. Actually you are going to get it. Now at any instant the displacement is nothing but the sum of all the individual displacements together. Now if I add it all these things together, which will be equal to the initial displacement, that's what we have given to it. Got it or not? The method of converting this particular wave, that is a triangular wave, into the form of sinusoidal and cosinusoidal waves is called the Fourier series. That is a beautiful tool. So which will convert, given a random curve, whatever may be the curve you can think of, you give me the equation, I will convert into the sum of cosines and sines. So that is given by a tool called Fourier series. Now here, for the given solution, that is y of x comma t, so this is f of x value is coming out to mu x into L minus x. This is not a sinusoidal wave. Now this can be converted into a sinusoidal wave with the help of Fourier series. So by assuming here actually there are infinite possible harmonics are there. So for different values of n, different harmonics you will get. We get it. Right? Different frequencies you are going to get it. Obviously, right? Understood or not? So that's why actually when we are analyzing a non-sinusoidal wave, you have to analyze for all the waveforms or all the harmonics together. Suppose if it is a sine, then obviously there will be only one sine, actually it is going to move in this particular format. Got it? With one frequency. But here actually there are infinite frequencies that are coming to picture. All the frequencies together will make that initial wave. Now here, y of, so x comma 0, this value sigma n is equal to 1 to n and bn. So x comma 0 sin n pi x by L. So this is 1, right? So this value, it was given as initially f of x value is mu x into L minus x. And this is very important to understand. Got it? Now actually, if this is the case, expressing this into this particular format we call as the Fourier series. Expressing sum of mu x into L minus x into the sum of sine wave is called Fourier series, or to be specific, half range Fourier series. So I will give the knowledge of Fourier series to the extent whatever we need for this wave equation or the heat equation. But actually Fourier series, that itself is a very big topic, right? In that actually we will be using only half range Fourier sine series or half range Fourier cosine series, right? So here actually in this case we are going to use only half range Fourier series. So that will be to find out this Bn value. So we expressed this into the sum of this one. This method is called as the Fourier series. Now actually this Bn value we have to identify so that it fits for this equation. And for that actually we have a standard method to find out this Bn value. Got it? Do you have any questions on this? Any questions on this? Okay, so note down till this point. So I am going to find out the Bn value with the help of this equation. See this, the initial limits actually that you have to make out on your own based on the conditions whatever he give it. That is, if this is a string, obviously the string is tied at this point and tied at this point, right? For this actually, you can make out two different boundary conditions. One condition is u of 0 comma t. So irrespective of the time, this is always tied at a 0 location. This is what we call as the node in case of static waves, I think, right? So this is a node, and this is also a node. Now at the nodes actually, the particles actually don't move from that particular location irrespective of the time. So at x is equal to 0 and this point is 0, y displacement is 0, and at x is equal to L also the displacement value is 0 irrespective of the time. These are actually standard boundary conditions for all the kind of waves. This is one thing. And another condition is, initial velocity actually we will be always taking as 0. The initial velocity, because we have not given the initial velocity, you just dragged it and left it. So dragging and leaving. So there actually you have not given any velocity. Just holding for some time and leaving will automatically create oscillations. That means initial displacement dy by dt value at t is equal to 0 is 0. That is one condition. And another condition is, initial shape, how he has stretched that string, that also has to be given by the problem statement itself. Depending on that only how these oscillations are going to be coming. So all the four conditions, four unknowns. So this is the standard method for this kind of wave equation. Got it? Noted down? Okay. Now this Bn value we will be finding it out. Now I will just write the important things. So our solution is y of x comma t is equal to b sigma bn into sin n pi x by L cos n pi c t by L. So this is the solution. And in this solution, this Bn value is unknown. To find out the Bn value, we will be using this. So as per the expansion of Fourier half range sine series. So why Fourier half range sine series is, here only we have sine. So only sine terms are there. Usually any Fourier series will contain both sine and cosines together. But actually here we have only cosine, only sines. That's the reason actually we say this as the half range sine series. So if the series contains only cosines, then we say half range cosine series. Now for this one, if you want to find out the Bn value, the standard method is, that is 2 by L times of integral 0 to L. So this is the range of the wave. So this is value. So this point mu x into L minus x is valid for the range of L. So this is the string and this is the initial displacement given by f of x is equal to mu x into L minus x. So this is within the range of x is from 0 to L. So for this, this is the equation. So if that is the case, 2 by total range. So this range is 0 to L. That means L minus 0 is the total range. So 2 by L. So 2 is always there. Half range cosine series always comes with 2. And then by L. 0 to L is the total range. And then the function value, that is sin n pi x. Sorry, the function value is mu x into L minus x into sin n pi x by L into dx. So this is the value of Bn for any kind of half range sine series. So in the half range sine series, this is the method to find out the constant value Bn. So this is 2 by L integral 0 to L mu x into L minus x into sin n pi x by L is as it is. So the product of these two and the limit is given by this range 2 by of that 2 by L 0 to L mu x into L minus x sin n by x by L into dx is nothing but bn value for different values of n. If n is equal to 1, you have to keep n is equal to 1. If n is equal to 2, you have to keep n is equal to 2. So we will derive a general solution for this. So this integral actually you have to do it. This integral value now is it fine? No? I think somewhere you can refresh it once. Okay, so this value you have to find this integral 2 pi L. Now when this integral is going to be, so u, this is mu also I will take it, 2 mu out, then x into L minus x. I take this as Lx 2 mu by L, integral 0 to L, Lx minus x square sin n pi x by L dx. Now this integral is going to be, so this is Lx minus x square into integral of this. This is integral sign minus cos n pi x by L minus derivative of this. This is L minus 2x into integral of this. That is integral cos minus sin n pi x by L divided by n pi by L whole square plus derivative of this is minus 2 and then integral of this is minus of minus, integral sign is minus cos. So that is cos n pi x by L divided by yeah, is it fine now? Is it fine? Avinash, Deepak, Liju? visible now? No video. I shared it again. Can you refresh? Lizu, can you refresh? Everybody, can you refresh once? Is it better now? Nitya, is it better now? Audio? I changed the battery just now. Is it clear? Deepak, is it clear? Okay. So, anything better, Avinash? Is it better now? Fine? Huh? Okay. So, is it better? Can I continue? Yeah. So, is that fine now?